Okay, let's continue our discussion. So we have here a table which is to have the value for case of A for the active earth pressure coefficient. So the values of case of A here, wherein our beta is 90 degrees and alpha is 0. So what is important is we have here, so that we can have the value for case of A, you just need the value for P prime, of course, and your small delta. And once you have that one, you can locate the value for case of A. So this is another, this is a continuation for the tabulation. So this one is the value for case of A, wherein we're given with the condition that the small delta is equal to phi prime all over 2. So we need the value for alpha, phi, and the beta, so that we can have the value for case of A. And for this one, this is of course an illustration for a Coulomb active pressure wherein there is a surcharge on the backfill. So if the surcharge, so we have here the inclined back face of the retaining wall. You have your inclined backfill with an angle of alpha, and of course your back face of the retaining wall has an angle of beta with respect to the horizontal. This one, the inclined backfill, is having an angle of alpha with respect to the horizontal. And of course, we're going to compute for, this is an illustration for the Coulomb active pressure having a surcharge on the backfill. So this is the surcharge, this is the backfill. So we have here a surcharge on the backfill. So to compute for our active force, we make use of this equation. So basically, you have the presence of your gamma is of Q, and the value to that is given by this expression. So this is the pressure distribution for our Coulomb active pressure with a surcharge on the backfill. So let's have an example here. Consider the retaining wall. You have consider the retaining wall shown in the figure in 12.12a. So having h equal to 5 meters, the unit weight of the soil is 17.6 kilonewton per cubic meter. The angle of friction of the soil is 35 degrees. The wall friction angle, which has small delta, is equal to 2/3 of phi prime, and the soil cohesion is 0, and alpha is 0, and beta is 90 degrees. So we have to calculate the Coulomb's active force per unit length of the wall. So for this one, so we're going to consider our figure, which is in 12.12a. So this is our figure for our sample problem. We are given with our beta, we are given with our small delta, and some of the parameters such as gamma, P prime, and C prime. So we're going to compute for the Coulomb active force for this particular problem. So that we can compute for the Coulomb active force per unit length of the wall, so we're going to make use of this equation. So the equation that you're going to use is 1/2 gamma h squared times case of A. So basically, we have to identify the value for our Coulomb active lateral earth coefficient denoted by case of A. So that we can have the value for case of A, we have to resolve that through our table, which is found on 12.6. We just have to identify our alpha, which is 0, beta is 90 degrees, and our P prime is 35 degrees. Our delta prime is 2/3 of P prime, which is 23.33 degrees. So basically, using that table 12.6, we can identify that case of A is equal to 0.2444. So once we have identified our case of A, we can substitute that one to our equation, and simplify, you get now the Coulomb active force per unit length of the wall, which is 53.77 kilonewton per meter. Okay, let's have another problem for this. We're going to refer to figure 12.13a. We're given with h equal to 20 feet, p prime is 30 degrees, small delta is 20 degrees, alpha is 5 degrees, delta is equal to 85 degrees, and our Q, surcharge, is 2,000 pounds per square feet. Gamma is 115 pounds per cubic feet. So we're going to determine the Coulomb active force and the location of the line of action of our resultant force. So basically for this example, we have to refer to figure 12.13. So 12.13 is given by this figure. So this is 12.13. So we are given with a retaining wall having a back face which is inclined with an angle of beta, and you have an inclined surcharge with an angle of alpha, and of course you have a backfill rather with an angle of alpha with respect to the horizontal, and of course there is a surcharge acting on the backfill. So the surcharge is on the backfill. So how to compute for our Coulomb active force and the location of the line of action of the resultant force? So we simply have to make use of our equation. So basically for this problem, we're going to solve for the total active force. So since we are having the total active force, we're going to make use of the pressure distribution of this figure 12.13. So this is our pressure distribution. So if we're going to make use of this, we're going to compute for the total active force. We simply have to get the area of this pressure distribution. So if we're going to get the area of this, so meaning to say, we're going to have two areas, area of the rectangle and area of the triangle. So basically, our Coulomb active force would be equivalent to, for this one, this is K sub AQ, quantity sine squared beta all over sine of quantity beta plus alpha times the height, which is h. Then this should be added to plus 1/2 of K sub A gamma times h sine beta times h. So that is the total active force for this particular figure. So if we're going to substitute the given values for the parameters, so we're going to have our Coulomb active force equal to 22,486.9 pounds per feet. Then if we're going to locate the line of action of the resultant, we simply have to resolve that through this equation. So our resultant P sub A times Z bar is equal to P sub A for the first figure plus P sub A for the second figure, multiply of course each of those figures to the distance from the centroid of that particular figure to our reference point. So for this one, our reference point is the bottom of the wall. So if we're going to substitute the given value, the values for the total forces for P sub A, which is our resultant, substitute this value, then equal to force total active force for the first figure, which is the area. So substitute that value times h all over 3. This is a rectangle. This is the triangle plus the rectangle. So you simply have to simplify. So we get now the location of the line of action of the resultant, which is 8.78 feet, which is measured vertically from the bottom of the wall. So let's move on now to lateral earth pressure due to surcharge. So how are we going to analyze for a lateral earth pressure due to surcharge? So for this one, we are given with two illustrations of the lateral earth pressure caused by a surcharge. The first one is you have a retaining wall, you have a backfill, and subjected to the retaining wall is subjected to a line load for the first figure. And the second figure, of course, this is a lateral pressure that is caused by a strip load. So this one is a line load for the first illustration. You have a retaining wall caused by the that is subjected to a line load. So basically, we're going to compute for the stress of on the retaining wall, the stress at any depth z on the retaining wall caused by a line load, and you're going to compute for the second figure. You're going to compute for the stress at any depth z on the retaining wall caused by a strip load. So basically for this, if we're going to have the first illustration, the stress, what would be the stress caused by the line load, the stress on the retaining wall at any depth z caused by the line load. So you are given with this expression. So this is the formula to compute for the stress at any depth z on the retaining wall caused by a line load. So you simply have to substitute. Of course, you have here our horizontal stress at any depth z, when z is equal to b times h. And basically for this, we have here the location for our BH and the location for our A sub h. So of course, our h is the height of the retaining wall. So if you're being done with the depth, wherein you're going to compute for the stress, you can have the value for B. And similarly, if you have the length or the distance from the retaining wall towards the line load, you can have you have the value for the retaining the height of the retaining wall. You can have the value for our A. So, however, if there is a condition that if A is greater than 0.4, you're going to make use of this equation. And if A is smaller or equal to 0.4, our stress for the computation of the stress is this expression. So that is the stress caused by a line load on the retaining wall. For the second figure, for this one, for the second figure here, this is a stress. What would be the stress on the retaining wall at any depth z caused by a strip load? So if we're going to have a strip load acting on the backfill, so you're going to have this equation. So this is the expression to compute for the horizontal stress at any depth z on the retaining wall caused by a strip load. So to compute for the total force per unit length due to the strip load, this is the equation. We have the presence of theta 1 and theta 2. To compute that one, we're going to use this formula so that we can have the value for theta 1 and theta 2, which is necessary to compute for the total force per unit length of the wall due to the strip loading. And for the location of the resultant force P, you're going to make use of this equation so that you can find the value for the location of the resultant on the retaining wall that is subjected to a strip loading.